Hi guys, this is Rich. I've been having trouble with my computer today, so I'm going to record this next section in individual pieces, and then I'm going to try and copy and paste them all together as one recording. At least that's the theory, so we'll see how well that works. This is a video from the XT111 course. I'm going to finish up with a limited scope of practice, and my topic is on page 8 today, image production, section C, criteria for image evaluation and technical factors, as well as part D, quality control of imaging equipment and accessories. And that from this edition of the limited scope of practice content specs from the 2011. So that being said, let's dive right in and start talking about exposure indicators. And this is a number called exposure index. The exposure index refers to the amount of exposure received by the image receptor, not by the patient, although it is commonly referred to as how much radiation the patient got. But in fact, exposure index is measured at the image receptor. Knowing how these exposure factors impact the exposure index is key to learning to provide enough exposure to the IR while limiting exposure to the patient. And so we use exposure index numbers to determine whether we have selected enough exposure for the patient, or if in fact we have too much or too little. Manufacturers differ in the way this number is represented, making it difficult to calculate exposure amounts. And so for many years, we in the clinical world have been calling for some kind of standardization for this, and we have finally come up with deviation index numbers, which I'm pretty sure we talked about in a lab, and so I'm going to try and define them as well. An understanding for exposure index means that you need to have a fundamental understanding of these terms: air kerma, standardized radiation exposure, K standard, indicated equivalent air kerma, K indicated, target, K target, and then deviation index. Briefly, let's talk about these. Air kerma is kinetic energy transferred from the photons, the radiation photons, to electrons during ionization and excitation. And this is going to be measured in the air at the image receptor. This is most often expressed as joules per kilogram, or the System International unit of Gray. The standardized radiation exposure is that which we would expect for a typical image receptor system. What is its baseline response to radiation? This exposure is made with additional filtration that hardens the beam to simulate patient tissue. And so this becomes a standard number, part of the algorithm when we calculate exposure index. Add to that the kerma indicated, which is boils down to the bottom bullet point. Simply stated, the indicated air kerma is the amount of exposure on the image receptor. Okay, so this is the actual number that the system measures and reports out to us. And then the target is a set of specific values that represents an optimal exposure for each body part and view. This is probably the standard that is inherently built into the lookup table. The lookup table has a certain expectation of how much exposure we will have. The KIND, the indicated, is how much we give it. And so then the exposure index takes a look at our exposure in relationship to what it expected, and that's how it reads out whether our exposure index is too much, too little, or within tolerance. Understand that exposure index number is not a specific number. It is not 550. It is a range of numbers, like for instance, between 100 and 200. Any exposure index between 100 and 200 is considered within exposure index tolerance. So the exposure index is a measure of the amount of X-ray exposure to an image receptor. And these EI calculations vary between manufacturers. Fuji, for instance, has an exposure index number of 200 to 400 is considered normal, and that is inversely proportional. So a number less than 200, a lower than 200 number indicates overexposure. A greater than 400 number indicates underexposure. Kodak Carestream has exposure index numbers, and those numbers, the optimal is about 2,000. So, and that's directly proportional. Numbers above 2,000 indicate too much exposure. Numbers less than 2,000 indicate not enough exposure. So these exposure index calculations vary between manufacturers, and this is why we as technologists are looking for a standardization of this whole mathematical gobbledygook, so that we have a clearer sense for in the unlikely event that we decide to repeat an exposure, do I need to use more exposure or less exposure? So when we evaluate our image, let's look at the image in totality. Let's look at not only the positioning and relevant anatomy on the image. Well, let's take a PA chest X-ray, for instance. I'm looking, do I have both lungs fields completely on there? Is it rotated by virtue of the fact that the sternoclavicular joints are equal and bilateral? Are the spinous processes equal and all in a column? Do I have quantum noise or quantum model on my image? And that will be indicative of my exposure index number. If it indicates underexposure, it's likely that I have a certain amount of quantum model on it. Okay? I'm looking for collimation. I'm looking for motion. I'm looking for distortion and resolution on my image. I'm looking for the brightness and the contrast. Although in the digital imaging environment, that should be pretty good. Artifacts on the image, something on the image which is not representative of the patient's anatomy. That's an artifact. I'm going to use the exposure index number as a frame of reference for the exposure to the detector. If you are satisfied with the image appearance based on the anatomy that you've demonstrated, and the exposure index number supports the look of the image, you are within tolerance, then you should feel comfortable in sending that image for interpretation. Send it to PACS. If your exposure index number is not within tolerance, well then perhaps the deviation index number can help you to determine what you need to do next. Deviation index number, that is developed by the American Association of Physicists in Medicine, and what they did was they came up with a system that establishes a range of exposure index variances based on the exposure index target. And they scaled it in increments of -6 to +6. Okay? With the center perfect is at 0. So if you have a deviation index number of +1, then that indicates that you are about 25% overexposed. +2, 50% overexposed. On the negative side, if you have a -1 or a -2, that's actually not 25%, that's actually 20%. There's a typo in here. But nonetheless, it is a direct relationship. Plus numbers indicate overexposure, minus numbers indicate anemic exposure. deviation index numbers of +3 or greater, that is considered an ALARA violation, and that is considered a cause for concern. All right, so let's talk a little bit about quantum noise or quantum model. Quantum model is based on the random nature by which X-rays interact with the image receptor. When quantum model is present, spatial resolution is lacking, and the image will look pixelated. Okay, and you will notice that on your screen, and you'll say, boy, that looks like there's quantum model in there. And quantum model is most easily remedied by using more MAS, and by using more MAS, that increases the signal to noise ratio, and it fills in that pixelated appearance and gives us the spatial resolution that we need. Now we can use higher MAS, we can use lower KV, we can use slower image receptors, which reduce quantum model, but some of those are more attuned to the film screen environment, and we're in the digital environment. And so with the digital environment, we do have the opportunity to use higher KV, and by using higher KV, we can use less MAS, and that will decrease patient dose. Nonetheless, if you have a quantum model-y image, that is indicative of you probably have a low exposure index number, indicates that there was not enough exposure, and so you would want to increase MAS to eliminate that quantum noise, that quantum model. Noise is background information received by the image receptor. And to some extent, electronically, we can filter out that noise if it's less than the incoming signal. We have several different kinds of noise. We have system noise, and system noise comes from the electronic components in our X-ray room. Have you been in an X-ray room? Do you hear the electronic equipment humming in the background? And sometimes that causes some interference, which shows up on our X-ray image. We also have ambient noise based on background radiation. Perhaps you left a CR plate in the X-ray room and it was exposed to a little bit of scatter radiation. That will show up as fog or ambient noise on your image receptor. And finally, there's quantum noise that we've been talking about, and quantum noise is typically a lack of MAS, a lack of exposure. Noise is expressed as signal-to-noise ratio, SNR, quantified as a numeric value. And I talked a bit about signal-to-noise ratio in another video. Bear in mind that higher signal-to-noise ratio is desirable for the digital environment. We would like to have high signal-to-noise ratio, which is indicative of a quality radiograph, versus low signal-to-noise ratio. Well, there we're going to have some level of quantum model, and that's not a good thing on our digital image. Also, noise does contribute to contrast to noise ratio. Contrast to noise ratio is the ability to see lots of different grays, even if those gray values are very close to one another. And so that is contrast to noise ratio, which is probably not going to be on your certification exam, but be aware that contrast resolution, the ability to see subtle gray shades, contributes to some extent to spatial resolution. An example of that would be the fat pads on the elbow. If we can see the individual grayscale of the fat pads or not see them, then that is indicative of perhaps there is or there is not an occult fracture of the elbow. And so from that perspective, we would like to see contrast to noise ratio at a high level so that we can see the subtle shades of gray. Here is another issue, and that is gross exposure error data drop artifacts due to the detector element or the pixel saturation and excessive exposure. Turn your attention to the left iliac crest on this pelvis x-ray, and can you see that the iliac crest seems to be missing a portion? And clinical correlation with this patient indicates that they did not have a lytic or a metastatic disease process going on. In fact, what has happened is we overexposed this patient so much that the detector elements were so exposed that all they had was dark. They were not representative of where that anatomy represented by what grayscale. So from that perspective, what we have here is a gross exposure error. Take a look down at the greater trochanter on that same left side. Can you see that the same thing was happening there? And so what can we do to correct this? Well, there are some post-processing and pixel recovery algorithms that we might be able to run this through, and that may restore some of that visibility of detail. We could columnate this more carefully so that we had less scatter radiation. We could offer some kind of compensating filtration to attenuate some of the X-ray in that area of anatomy, and by doing that, we would be able to perhaps compensate for this error. All right, I'm going to stop here for a moment and take it up with the next video. I will see you back in 1 minute.